Performance is often treated like a feature you add later, something you tune, optimize, or fix after the system exists. That framing is wrong. Performance is not something you sprinkle on top of code. It's a consequence of how execution behaves over time. Every decision choice shapes the work the CPU must do. You don't optimize your way out of a bad execution shape. You feel it in latency cost and instability. To understand performance, we need to stop thinking about code as text and start thinking about it as motion. The CPU does not see services, layers, patterns, or intentions. It sees instructions, loads, stores, jumps, calls, returns. Every abstraction collapses into those primitives. This is why performance discussions that start with architecture diagrams often fail. They're one level too high. The CPU doesn't execute diagrams. It executes steps. If you want predictable performance, you must design with the CPU's experience in mind, not yours. One of the most common performance failures come from code that looks beautiful but behaves poorly. Clean abstractions compress complexity for humans, but they don't remove work. When systems slow down, teams are often surprised because nothing looks wrong. That surprise is a signal. The cause was hidden. When performance collapses without obvious hotspots, it's usually because execution shape was never examined. Only code style was. Abstraction doesn't stack cleanly. It multiplies. Each layer adds calls, branches, checks, and memory movement. Individually, those calls look small. Collectively, they dominate runtime. This is why performance issues often scale non-linearly. A small increase in traffic suddenly causes a large increase in latency. The system is doing slightly more work. It's traversing the same expensive paths more frequently. This is the most important performance rule. Faster execution doesn't come from making instructions faster. It comes from executing fewer of them. Skipping work always beats optimizing work. This is why structural changes outperform micro-optimizations. When you remove entire branches, calls, or paths, you eliminate cost completely. That's real performance improvement. Everything else is incremental. In almost every system, most executions follow the same path. That path defines your performance profile. Rare edge cases don't matter unless they become common. Yet many systems are designed to handle every case equally, paying cost up front even when it's unnecessary. Performance-aware design starts by identifying the dominant flow and making it as short and predictable as possible. Early exits change execution dramatically. They turn long paths into short ones. Guard clauses, validation gates, and fast failures aren't defensive programming habits. They're performance tools. By rejecting work early, you preserve CPU time, memory, and downstream capacity. This is why high-throughput systems aggressively fail fast. They protect the common path by killing bad ones quickly. Procedural code aligns naturally with performance because it makes execution order explicit. There's a beginning, a sequence, and an end. No hidden dispatch. No implicit behavior. This doesn't mean object-oriented design is wrong. It means that when performance matters, systems tend to flatten into procedural shapes. The CPU thrives on predictability, and procedural flow provides exactly that. Microservices make performance cost impossible to ignore. Network latency. Network latency, serialization, and cold starts amplify every inefficiency. That's why microservices often look procedural inside. Validate, act, return. Anything extra becomes visible pain. The environment forces execution honestly. You either control flow tightly, or the system punishes you, immediately. Another common failure is building clever pipelines that do too much too early. Parallel steps fire before it's clear they're needed. Resources are consumed speculatively. Under load, these systems collapse because they multiplied work instead of controlling it. Parallelism amplifies bad flow. Without strict gating, it makes performance worse, not better. Here's the repeatable method. Trace execution first. Identify the dominant path. Count steps. Ask what can be skipped, rejected, or delayed. Only after flow is correct does micro-optimization matter. Profilers don't replace this thinking, they confirm it. Performance emerges from design clarity, not tools. When developers shift from designing code that looks good to code that executes well, everything changes. Abstractions become deliberate, flow becomes explicit. Performance stops being mysterious. This isn't about writing low-level code everywhere. It's about respecting execution reality when structured decisions are made. Once you internalize this model, performance stops being reactive. You can reason about it before running code. You can spot danger early. You design systems that age well under load instead of collapsing unexpectedly. This is a difference between chasing performance bugs and preventing them. The fastest, most reliable systems aren't clever. They're boring, explicit, and disciplined about execution. They respect the CPU's simplicity instead of fighting it. Performance doesn't come from brilliance. It comes from restraint. If you want fast systems, design execution paths that are easy for a boring machine to run.